it was just another example where what did we show you? We showed you loop invariants are good. We did a little kick on running time. And all right. I'm not sure why this is here, because this is a recursive program. And but I suppose you could have an iterative version of it. I would do this more when we were doing recursion, but so if you want to print all the numbers in a tree, you can print them in different orders, right? And prefix order is you handle the left tree, then you do, prefix. Prefix is you do the root first, right? You do the root, then the left and the right, right? Postfix, you do the left, the right, and the root. And infix, you do the left, right? You put it in the middle, left, root, right? So you can kind of, see these various trees, all right? So if you look down at this tree here, as we read, so this is pre, we do the root first, right? 5. And then we're going to do this guy's tree, so we do its root first. And then we do its root first. So we're going 5, 3, 1, 2. Oh, now we finished here, so we do 4, 6. Right? Yeah. Yeah, so we do his right, and then we do her right, and then we do her right. Right? Versus if we were doing postfix. In fact, when I was in elementary school, just about getting to high school, they came up with the first calculators that you could buy. And the first ones were, they were called reverse Polish notation. It's kind of like this, right? So how you go through it. Let's do this one in reverse Polish. You do 3, and then it goes on the stack. And then you go 4, and it goes on the stack. And then you do times, which multiplies them, right? And so now 12's on the stack. And then you put 7 on the stack, and then you do a plus, which adds the 7, right? So you're doing it reverse Polish, right? Versus infix, right, is 3, n is times 4 plus 7, right? In fact, infix is, imagine this is vertical, a vertical line sweeping across, right? And it does, the vertical line first hits the 3, then the times, then the plus, then the, right? People kind of get those orders a bit. We can struggle with them more in our lives, but I think the reason we're doing it, I didn't know why we were doing it, but here it is because we got a reverse Polish calculator, all right? So first, we see that the 1, and what do we do with the 1? We push it on the stack, right? And then we get the 4, we push it on the stack. Then we get the plus. So in the calculator, you go 3, 1, enter, 4, enter, plus, right? So when you get the plus, this is what I said. What happens? This gets popped off the stack, right? So here we're doing 1, 4, 2. Here I'm just saying the order in which they happen, right? So 1, 4 plus 2 times, right? That's the traversal, right? In this one, what's the traversal? 3, and now we have to do this side, right? Before we do the times last, right? So now we have to do this side. So we do the 1, and the times is second last, right? So we have to do the 4, and then the plus, and then the 2, and then the times, followed by this times, right? I guess I'm doing here brackets, which means this tree, we do the left child, then we do the right child, and then we do the times on top, right? Does that make sense? And it has a recursive structure, but we're not doing recursion now, right? So we're given the string onto our calculator, right? And we have to calculate the output. And so what is the calculator, right? Here's the output, right? Of this, 1 plus 4 is 5, 1 plus 4 is 5, times 2 is 10, times 3 is 30, right? That's what we need to calculate. Are people following what we're doing here? So you can imagine you're in elementary school and you're given one of these calculators, right? You've never seen a calculator before. All right, so how do you do it? Well, we're going to, so here's just, remember when we did do recursion, and how did we implement it? With stack frames, right? So they were done with a stack. And so what we're learning here about is stacks. So we're going to do the stack. So here's our stack. And what's our loop invariant, right? A loop invariant is we're going to read the guy in order, right? So we've read some prefix. And as you go, what's our step is that you push things on the stack, right? So you get 1, it goes on the stack, right? And as you go, the calculator is holding the stack, right? So then you get 1 plus 4, right? 1, 4, right? So what happens? Well, I guess I'm going a little quickly here. All this happens and the 10 goes on the stack, right? Because that all evaluates the 10. And then you pop these two, when you see the times, you pop these two numbers and multiply them and put the result on the stack, right? So I think hopefully we'll do it again, but in more detail, right? The 3 goes on, the 1 goes on, the 4 goes on, right? And then we get a plus. So what does the plus do? Plus says, pop the top 2 numbers and add them, right? So that's what we do. We add them and we pop the 1 and the 4 off and we push the 5 on, right? So now you can see what's on the stack is the 3 and the 5, right? So then we get a 2 and the 2 goes on the stack. And then we get a times. And what does the times do? It pops the 2, it pops the 5, multiplies them, and puts the 10 onto the stack, right? So now what we have is the 5 and the 10 on these. The 3 is sort of by itself, right? And the 10 is this little subtree. And we have their value, they're independent things, and they're on the stack, right? And so you can imagine what the loop invariant here is, right? And then we get a times, and at this point, what do we do with this times? We pop the 10, we pop the 3, we push the 30 on the stack, right? Does that make sense? Are people following this? Right, so what are we trying to learn here? Again, you can have very complicated algorithms, but if you sort of define the loop invariant, and what would the loop invariant be in this case, is I'm building up these little trees, and every separate tree has been evaluated, and the values of those separate trees are on the stack, right? Everybody good? And you might, if you go back here, how did I develop? Well, I didn't develop this algorithm. It was clearly before me. But here I'm doing it in bigger steps, and I'm thinking, okay, what do I want to be true right now, right? I'm designing my loop invariant. What I'm trying to do now is I've read the left tree, I've read the right tree. My loop invariant is that I've evaluated them, and I'm ready to get the time. And so where I've evaluated them, where are those values, right? Those values are on the stack, right? That's kind of my loop invariant. And then when I get a times, right, it merges these two trees. So I have to pop things off the stack. Sorry, people in the world. My mic fell, and that would have been very loud for you. All right, everybody good? So you can see how what I was doing here was I was jumping. I know that I'm reading the left tree in. So what do I want the loop invariant? I read in the right tree. What do I want the loop invariant to be? I read in the times. What do I want the loop invariant to be? So I'm sort of building up the loop invariant that conceptually, right? And that helps me then to say, well, how do I do the subtrees now? Right? Does that make sense? This is all, the purpose of this is to kind of help you design new algorithms, right? And describe the algorithms in ways, right? And you'll see we didn't give you any code, and you more or less get the algorithm.